Hey guys, welcome back to chapter 8. Today we're going to talk about the last reaction that you guys are responsible for. And then we're going to apply that reaction to one of the more difficult problems in this chapter. Problems called titration problems. So this is what your lab is going to ask you to do for this chapter. So titrations. Titrations typically involved acid-base reactions. So like I said, this is your fourth and final reaction that you're responsible for. It's an acid-base reaction. So we're going to react an acid and a base together in the presence of water. Now, I understand that we haven't talked about acids and bases before, and we really won't talk about them in much detail in this chapter. We get to that in the second half of this course, so general chemistry 2. But just a brief introduction to acids and bases and the way that I will always put them together in this chapter. So an acid is going to be something that produces hydrogen ions when it's dissolved in water. So acids dissolve in water very much like ionic compounds do. So they dissociate or they break apart into their ions. When they break apart into their ions, one of the ions that they produce in solution is this hydrogen ion. So that's going to be one of your indications that that is in fact an acid, because many acids begin with the letter H. So the classic example here that you see is hydrochloric acid, HCl. So that H is going to be dissociate or break apart from the chlorines. So there's our hydrogen ions. That's how we recognize an acid. I'll also help you with this. So throughout the chapter, I'll say something like the acid, hydrochloric acid, reacts with the base. So I'm going to help you out with identifying acids and bases in this chapter. Bases, let's ignore this first statement here. We'll talk about that in the second half of the of general chemistry. But for bases are going to also dissolve in water. They're also going to do so by dissociating. And when they dissociate, they are going to produce hydroxide ions in that water. So the poster child for a base is sodium hydroxide. So sodium hydroxide we know is an ionic compound. It will dissociate when dissolved in water. And when it dissociates, that's where we see those hydroxide ions that form as it dissociates. Okay, so that's your acids and bases in a nutshell. Like I said, I'm going to help you out with this chapter. So you'll be able to identify acid-base reactions because I'll say something like hydrochloric acid reacts with the base sodium hydroxide. Okay, so that'll be your tip there. So the reaction that you are responsible for are acid-base reactions, also known as neutralization reactions. So a neutralization reaction is when an acid is mixed with a base, and it will always form the same products. It will always form water, that's always going to be present, and then some sort of ionic salt. So when I say salt, you probably picture sodium chloride. But when we use the word salt in chemistry, all we mean is an ionic compound that'll dissolve in water. So a salt could be sodium chloride. That absolutely is an example. A salt could also be barium chloride or magnesium chloride. Or potassium iodide. So any ionic compound we could refer to as a salt. So don't automatically write NaCl. It depends on what we're reacting together. So we'll look at an example in just a minute. Okay. So neutralization reaction, acid reacts with base to form water and some sort of salt. Okay. So let's look at an example really quick. Let me just kind of make one up off the top of my head. So let's take the acid. Let's take hydrofluoric acid. Reacts with the base barium hydroxide. Actually, no, let's make life easy. Let's do potassium. Okay. All right. So how do we predict what the products are going to be? So hydrofluoric acid reacts with the base sodium hydroxide. So we know that water is going to be one of the products, okay? Where does that water come from, okay? Well, how that water is formed is that it's going to take the hydrogen from the acid. It's going to take the hydroxide from the base. So H plus OH gives us H2O. So that's how we get the water. So how do we predict what the salt is going to be, what the ionic compound is? Well, we're going to take whatever's left. So we're going to take the fluorine from the hydrofluoric acid. We're going to take the potassium from the potassium hydroxide. And this is going to be the salt that forms. We always draw the metal first, then the nonmetal. Okay? So this is the salt that forms from this reaction. We also have to consider the charges. So potassium is a +1, fluorine is a -1. So I can just write KF, and those are electrically neutral. That's a balanced salt. Okay. So that's a neutralization reaction, and that's the fourth and final reaction that you guys will need to predict the products and then be able to correctly balance that equation. So why do we learn acid-base reactions here if we're not going to talk about acids and bases? Well, we learn about them because they are the most common reaction used for the skill that we want to learn next. So the skill that we want to talk about next is titration. So a titration is when you take a substance of a known concentration and react it with another substance of an unknown concentration. And the whole purpose of the titration exercise is to determine the concentration of the unknown. That's the purpose. We start with what we know, and we use that to get to what we don't know. So that's a titration. Very often, titrations are acid-base titrations are probably the easiest ones. There are other types of titrations that exist, and as you get to higher level chemistry courses, you'll do those types of titrations as well. You also have fancier equipment to be able to monitor those titrations. But right now, let's talk about an acid-base titration. So here's the process of a titration. So we're going to mix hydrochloric acid with sodium hydroxide, and then in this beaker, we're going to have water and sodium chloride, okay? In this particular experiment, we've got some different glassware I'm going to talk about. So this glassware, let me get my pointer here. This glassware right here is called a burette. Okay, so a burette is going to help us to measure how much of this liquid we're putting in. So it might be full at 10 milliliters up here, and then we'll let it go down, and it might read 5 milliliters here. And we know that we then put 5 milliliters of solution in. So that's how a burette works. Okay. So in the burette is going to go our known. Okay, so we know the concentration of whatever is in our burette. Down here in our flask is going to be our unknown. Okay. So what we're going to do is we are going to mix our known with our unknown. The other thing I want to point out about our unknown here, we don't know what the concentration is of this. But we're going to measure with some precision how much we put in here. So I'm going to know that I put exactly 50 milliliters of that unknown in there. So I know how much is in there, right? All right, so we're going to mix our known with our unknown. So we open up the burette, we let it drip into this beaker. So if you were to do this in the laboratory, you would open it up, close it, open it up, close it, open it up, close it. It's a very tedious process, right? So as you guys are opening and closing, you're going to want to find what's called the equivalence point. And I have this in words in just a second, but the equivalence point is when the number of moles of our known and the number of moles of our unknown is the same, is equal. And that's going to be an important moment when we go to math this. So when we do our titrations, there's got to be some sort of indicator that tells us when we hit that moment, right? I don't know that just by looking at these two clear liquids. So in our acid-base titrations, we're going to have some sort of indicator in there that changes color when they're equal. So why we use acids and bases is because pH is pretty easy to manipulate. So when a pH switches from acidic to basic, we can have some sort of indicator in there that changes color right at that switch. That's the equivalence point. So that's why acid base is important here. So what we would do is we would open this up and close it, open it and close it, open it and close it until we see that solution. The moment that solution turns pink, boom, we shut our experiment down. We close it up, we're done. Okay? So just some terminology here. The titrant is going to be the solution that we know the concentration of. That's going to be up here in our burettes. That's called the titrant. And then, as I said before, the equivalence point is when the number of moles of the titrant is stoichiometrically equal. What a long word. Stoichiometrically equal to what is being analyzed. Stoichiometrically equal. So this word should clue us in that we're going to use a balanced chemical equation. We're going to use the relationship between the coefficients. We're going to use stoichiometry to solve these problems. So that stoichiometrically equal just means we're going to do our mole to mole ratio. Okay, so remember this map, grams of A, moles of A, moles of B, grams of B. What we're going to do is we're just going to do this step right here. Okay? That's what this stoichiometrically equal means. That's the step we're going to use. Okay? All right, so best way to get used to these problems is just to dive in. The other thing that I would do with these problems is, especially after you do your lab, this is probably one of the only problems in this semester of chemistry that I highly recommend drawing a picture. Well, I think if you draw a picture, it'll be a much easier problem to solve. Suppose we have 22.4 milliliters of 0.1 molar sodium hydroxide. That's how much was needed to reach the equivalence point when we mixed it with 100 milliliters of unknown HCl or hydrochloric acid. So it's asking us to determine the concentration of hydrochloric acid. Okay, so let's draw our picture so we can see what's going on here. So here's our burette. Here's our flask. Right? In our burette, right, is where our known goes. So 0.1 molar sodium hydroxide. So in here is our 0.1 molar sodium hydroxide. And we can also write down how much of that we use. So we open it up, closed it, open it up, closed it, open it up, closed it, turn pink, stop. After we stopped, 22.4 mils ended up in being used. So 22.40 milliliters. Okay. All right, down here in the bottom of our flask, this is going to be our unknown concentration. Okay, so we don't know the concentration. But what do we know? Well, we know what it is, right? We know it's hydrochloric acid, right? Unknown hydrochloric acid. And we also know how much is in there, right? So we put 100 milliliters of this hydrochloric acid in there. So we know it's hydrochloric acid, and we know there's 100 milliliters. Okay. So there's our picture, and that's going to be really helpful for us as we solve this. How do we solve titrations? If you can remember this mantra, it will be extremely beneficial as you start to solve these problems. So the mantra that I use for titrations is molarity, moles, molarity. Okay? So step 1, molarity. Step 2, moles. Step 3, molarity. Okay. So step 1, we're going to do the molarity equation. So molarity equals N over V. And this is going to be of our known. Right? It makes sense to start with what we know. Okay. Moles. Here's where we're going to do that mole to mole ratio. So we're going to go from moles of A to moles of B. And this is where we're going to go from known to unknown. Okay. So moles of A will be whatever we know the molarity of. Moles of B will be whatever we're trying to solve for. And so that's how we'll get from one unit to the other, right? And then lastly, we're going to use the molarity equation again. But this time we're going to plug in information about the unknown. And what was the whole purpose of this exercise? What's the whole thing that we're trying to solve for? Yeah, we're trying to solve for molarity. So we're going to know moles, we're going to know volume, and we're going to try to solve for molarity in that step. Okay? Molarity, moles, molarity. Okay? So let's go ahead and dive in here. All right. Step 1, molarity of our known. Okay, so we know we're using that equation. Let's take inventory of what we know and try to determine what we're going to solve for. Okay. Do we know the molarity of our sodium hydroxide? Yeah, that's what makes it our known, right? So the molarity is 0.1 molar. Okay. Any mention in this problem about the number of moles? No. So no grams, no moles. That must be what we're solving for. Any mention of the volume of sodium hydroxide that we used? Well, yeah, that's what the whole purpose of the burette, right? We open it up, we closed it, we open it up, we closed it, we open it up, we closed it, and we could gauge how much we used. Okay? That's something to think about here. What unit is this? Yeah, it's volume. What unit do we use for volume? Liters. Okay. So I'm not going to write 22.4 milliliters down. Nope. I've got to do the conversion to liters. So this is going to be 0.0240 liters. So make sure you're using the unit liters in your equations. By the end of this chapter, you're going to be able to go from liters to milliliters in your sleep. So just practice that and it'll be easy for you. Oops. All right, so we've got molarity, we've got volume. We must be solving for moles, okay? So let's plug and chug. 0.1 molar equals number of moles and our volume on the bottom. Right, to solve for moles, we're going to get N by itself. So I'm going to multiply by 0.02240 liters. Whatever I do to the right side, I also have to do to the left side. So 0.02240 liters. Okay. So N equals, so 0.02240 times 0.1 equals 0.00224, and the unit is moles. And let's make our life easy. Moles of what? NaOH. So that's why this picture is helpful, because I can just glance up to the left here and I can see, oh, we were using NaOH in that case. All right, so now that we've had a second to settle in with that, step one, molarity, and we solved for number of moles, okay? What was step two? Molarity, moles, molarity, okay? So let me erase this. I'm going to leave my answer. All right. So step two was moles, molarity, moles, molarity. This is where we were doing the mole to mole ratio. So moles of A to moles of B, known to unknown, right? Okay. So what we're going to do in this step is we're going to use the balanced chemical equation. And we're going to go from moles of sodium hydroxide to moles of hydrochloric acid. Okay, so ultimately we want to know what the concentration of hydrochloric acid is. Well, we need some way to get to that unit, right? So this is how we're going to do it. I'm going to start a train track with this answer, 0.00224 moles of NaOH. Draw my train track. Moles of NaOH are going to go on the bottom. And what do you think is going to go on the top? Yeah, moles of our unknown. So moles of hydrochloric acid. Okay. In our mole-to-mole ratio, where do we get the numbers that we input? We get them from the balanced chemical equation. So we started off easy here. So the coefficient on sodium hydroxide is 1. Coefficient on hydrochloric acid is 1. That is not always going to be the case. So you have to do this step. There are videos out there on the internet that will show you a different way to do this, and they will skip this step because they are using a 1-to-1 ratio. If and when I give you a problem that is not a 1-to-1 ratio, you have to solve it this way, okay? All right, so this one is an easy one. It happens to be a 1-to-1 ratio. So multiply across the top, divide by the bottom. Moles of NaOH cancel. So we've got the same number, 0.00224. But now that indicates moles of HCl, okay? So step 2 is a unit conversion, converting from unit of moles of known to the unit of moles of our unknown. All right, so we'll leave this here. Erase. All right, so our mantra, molarity, moles back to molarity. Step 3. Okay. So this time we're going to do molarity equation again. So M in V. But now we're going to put in information about HCl. We're going to put information in about hydrochloric acid. So the whole purpose of this exercise is to solve for molarity. So that's probably going to be our unknown. Do we know the number of moles of HCl that was used? We just solved for that, right? There's no mention of it in the problem, but that's what step 2 was helping us do. So 0.00224 moles. And then volume. Do we know the volume? Well, yeah, we do. We know how much we started with, but we're not going to put milliliters, are we? No. We're going to convert that to liters. So 0.1 liters of HCl. Okay. So I'm going to erase this because we've got it in our inventory. So now it's plug and chug. Plug it into the problem, chug your way through it. So molarity equals number of moles, 0.00224 moles, divided by the volume, 0.1 liters. So what is the molarity of the hydrochloric acid? 0.00224 divided by 0.1 equals, I just dropped my pen. So we get 0.0224 molar solution of HCl. All right, so that is a titration problem. A lot going on there, right? So again, this is my mantra. You are going to have to practice these. Practice. I'm going to force you to practice because I'm giving you them in your lab, right? So I'm forcing you to do it in your lab, but I would certainly seek out other opportunities to practice, okay? So I hope you guys found this helpful.